Hi everyone, so let us solve a new problem now. Here in this problem, we will learn about a very important property of a binary tree. So let's look at the problem. It says that we have been given a binary tree, and now what we have to do is we have to find its height. Okay, so guys, I have already talked about height of a tree in previous lectures. So just pause, take an example and think how it can be computed. Let's do that. Okay guys, so the definition of the height is that it is equal to maximum length of root to leaf path, right? So first thing to focus is this root to leaf path. So in any tree there is one and only one root, but it can have multiple leaves. So there will be multiple paths going from root to those leaves. Now out of all those paths, that path which has the maximum size or maximum length, that will correspond to my height. So let us take a quick example. So if I give you a binary tree which contains, let's say, these nodes, and then I ask you, tell me the height of this tree. What will be the answer? Just pause and think. So guys, here there are several root to leaf paths. First, let us identify the leaves. These are the three leaves. This is one root to leaf path, this is another root to leaf path, and this is another root to leaf path. Out of all these three paths that I have just shown you, this path looks like the longest one. And what is the length of this path? Just pause and think. So guys, now this is an important question that needs to be answered. How is length being defined? So sometimes people define length in terms of the number of nodes that appear along that path. So here, if I count the number of nodes that appear along this path, my output, which is my height, should be 4. But sometimes people say that, hey, by length I mean the number of edges along that path. So if you were to count the number of edges, your answer would be 3. So it depends upon what the question is asking. So here let us adopt a particular convention. So here by length, I mean number of nodes along that path. So here number of nodes is 4 along this maximum size path. So my output should be 4. As simple as that. Now you have to think how to solve this problem. So just pause and without thinking much, start thinking recursively. Let's do that. Okay guys, one thing that we understand and we can very confidently conclude from here is that whatever will be that path which will correspond to my height will definitely pass through my root, right? Because this is being defined that the path will go from root to some leaf, and because there is only one root, root will definitely participate in that path and hence will influence the value of the answer. So because root itself is a node, so I can say that, hey, my answer will be 1 plus something. Now what that something will be, that I do not know, because I don't know which nodes down the line will end up getting into the actual path that corresponds to my answer. But this one is for sure, this is the contribution of my overall root, right? Now, how to decide this something? So just pause and think, can you break the problem of finding height of this big tree into some smaller recursive problems where you find the height of smaller subtrees? Is that possible? Just pause and think. So guys, we are going to do nothing special over here. Again, we are going to model this problem as if this tree has a root, a left subtree, and a right subtree. So let's say there is an input where this is my root, and then this entire thing is my left subtree, and this entire thing is my right subtree. Now answer me one thing. If I know the height of my left subtree, let's say that height is h1, and if I also know the height of my right subtree, let's say that is h2, can you conclude the height of your entire tree if you know these two heights? Just pause and think over it. The answer is yes, quite easily, because I can say that, hey, whatever will be max of these two heights, I'll be happy enough to consider that path, and I'll add 1 to it. This 1 is for the contribution of this node itself. So this something which was mysterious is now no longer mysterious, considering the fact that if we calculate h1 and h2 in the correct manner. Okay, so guys, if I have to write this relationship, how can I write it? So let's take a try at it. So if I define a function height and pass some node to it, then let us define it in this manner. Height of a node should be equals to the height of the subtree which is rooted at that particular node. For example, height corresponding to this node, what do you feel it should be? Just pause and think of it. So when I say height corresponding to this node, I'm asking you to just consider this much subtree and forget about everything else. So if you just focus on this much of subtree, the height of this is 2. So height at this particular node should be 2. The height at this particular node should be 1, right? Because there is only one root and one leaf in this much subtree. And so there is just one path and there is only one node along that, right? So this is the way I'm defining it. Now, if I follow this convention, I can say that, hey, height of a tree rooted at, let's say this root, is equals to 1 plus, it is dependent upon the height of my left subtree and height of my right subtree. Okay, so first let us try writing the expression for height of your left subtree. Your left subtree is rooted at root left, so you can write it in this manner. And similarly, your right subtree is rooted at root right. Okay, and now whatever is maximum of these both, that will be picked, plus 1 will be the height of your actual input, right? So this is how I can go on, and based on this I can very easily write a recursive approach, right? Now guys, the next thing is, what will be the termination condition over here? Just pause and think. Okay guys, so when you write your code based on this logic, from root you are migrating to root left, root right, so you're kind of coming down. So eventually you will hit null. Now whenever you hit null, let's say you say height of null, it means that you are trying to evaluate height of a tree which is empty. Height of a tree which is empty should be 0. So I can say that, hey, if ever root is null, just return 0. As simple as that. So this will be my recurrence relation and this will be my termination condition, and job done, right? So guys, if you want, just do a dry run of this approach on this particular input, see how things are being returned, and based on that, just go ahead and write the code. Let's do that. Okay guys, so let us see how things will look if I do a dry run over this input. So you want to first call your function height at this node 5. From here, you will make a call to your left subtree, because the first call you will make will be a recursive call for your left, and then later you will make it for your right subtree, which is f of 1. Now from f of 2 again, the left node is 1, so you will make a call for f of 1, and then later you will make a call for f of 3. So you came from here to here, here to here. Now again from here, you will make a call to the left child of 1, which is null, and then later you will make here. What should this call return? Based on the condition that we have, I should be returning 0 from here, right? Because if I consider the subtree which is rooted at, let's say, the left child of it, then that is empty. So the height of that is 0. So it is perfectly legitimate to return 0. With the same logic, 0 can be returned here as well. Now what should this return? So your termination condition has been tested, how it is returning things in an appropriate manner. Now when you look at your recurrence relation, you can say that, hey, for other nodes which were non-null nodes, return 1 plus max of the values that you get from left call and right call. So you are getting 0 and 0 from left and right call, and what you will return will be 1 plus max of 0, 0, which is 1. So you will end up returning 1 from here, and that is absolutely right. Why? Because height of the tree rooted over here is 1, and returning 1 is perfectly right. Similarly, now once you make a call to f of 3, from this f of 3 you will make a call to f of 7, and now from f of 7 you will make a call to f of null here and f of null here. Similar thing that happened over here will happen here as well. You return 0, return 0, and over here you return 1 plus max of 0, 0, which is 1. So again you return 1 from here. Okay, now look at this. So this is your f of 3. It made a call for its left child. Now it would make a call for the right child, which is f of null, and based on the termination condition it will return 0 from here. Now what will this return? It will return 1 plus max of 1, 0, which is nothing but 2. And again that is perfectly right, because when I examine the tree rooted over here, the height of that is 2. Now when I look here, it will return 1 plus max of this, this, which is going to be 3. And if you take a look, the height of the tree rooted at this 2 is 3 units. Cool. Similarly, it will keep on happening. Like here from f of 1, you will make a call to f of 9. Let me make a call like this to f of 9. And when you call f of 9, this will again call f of null, from where you will return 0, 0. And from here you will return 1 plus max of these, which is 1. And now from here you make a call to the right child of 1, which is f of null, and you return 0 from here. And from here what you return will be 1 plus max of this, this. So you return actually 2. And from here what you will return will be 1 plus max of this, this, which is 4. And that in reality is your answer. So guys, this is how this approach would work. Now that this is clear, I can perfectly go ahead and write recursive logic for it. What do you believe will be the time and space complexity? Just pause and think. So guys, here again, every node is being touched exactly once. Now whenever you touch a node, what is the amount of work that you do there? Nothing more, right? You just receive the answers from left and right. After you have received them, you just compute their max, and then whatever result you get, you add that to 1. Finding max of two numbers is constant time operation. Adding that to 1 is also constant time operation. So I can say at every node I am doing constant work. There are n nodes, so my answer should just be order of n. Okay, so now just pause and try writing the code of it on your own. Let's do that. Okay guys, so let us see how the code would look like. So let's say there is a function called as max height, and this function intakes the root of the tree whose height is to be calculated. Now I can have a logic that, hey, if my root is null, which is my termination condition, I would just return 0. Otherwise, what do you think should we do? Otherwise, first we should make a call to the left child and get the left height. Then we should make a call to right child and get the right height. So let's get that done. So int left height equals to max height of the subtree rooted at root left. In exact similar manner, int right height equals to max height of the tree which is rooted at root right. And now what you will return will be 1 plus max of LH, RH. Job done. So guys, time complexity of this code is absolutely clear. What do you think will be space complexity? So just pause and think. Looking at the recursion tree diagram, it absolutely looks that the recursion tree diagram will be exactly same as the tree. So whatever will be the height of the tree, that would have been the size of your call stack in terms of maximum size at any instant of time, right? So order of h would be our space complexity. So guys, this is one elegant way to solve this problem where you do nothing special. You just break a problem of a big tree into sub-problems of smaller subtrees. So you divide and then you conquer. So that is what you do here, right? Now, the same kind of code can be written with a void function as well. So in case of void function, you just need to traverse the tree, right? And while traversing the tree itself, see if you can somehow detect the highest or the longest path that exists from root all the way till leaf. So just pause and think over it. Okay guys, so let's think of it in this manner. When I look at these nodes, I can imagine that they have some levels. I can say that, hey, this node 5 is at level 1. These two nodes are at level 2. These 3 nodes are at level 3 and this node is at level 4. So these are just the levels of these different nodes. Can I say that the node that has the maximum level, its level will correspond to my answer? Can I just say that? The answer is yes, and it's pretty much self-explanatory, because whatever maximum size path that you will have from root to some leaf, the leaf of that path will have the maximum level only. So think of it in this way. I'll just traverse the tree. While traversing the tree, what I'll do is, when I make the first call over here, I'll pass a variable called as level, which initially will be 1. Now, whenever I transition from root to root left and from root to root right, the new values of level that I'll pass will be level plus 1, right? Because I know it for sure that if I am the current node which is at level x, then both my children will be at level x plus 1, right? So this kind of logic I can have. And now I can say that whenever I reach leaf, then I'll check what is the instantaneous level over there. If that level is greater than my answer, I'll just update my answer. This is the idea that I can have. So just pause the video and try implementing this idea on your own. Okay guys, so if we have got to code this, what we'll do is, first we need to define a function signature. So this function is just a void function. Let's give it a name, get max height. And what does it take? It takes the root of the tree whose height is to be computed. And now, as we know, we need to pass level, right? And we need to track answer, right? So for all the different values of levels that we have seen so far, the maximum value needs to be somehow captured in this answer variable. Now, one thing that I know for sure is that because my leaf's level will only correspond to my answer, so I'll update this answer variable only if I am at a leaf. And I know how to check whether I am at leaf or not, right? So let's go ahead and write our code. First, you have your termination condition. Whenever you are coming down, 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 if you hit null, what do you need to do? Nothing. You can just return, right? Because if you hit a null, null is not some physical node, right? So whatever level that had is of no significance to you, right? So let's say if you got from 7 to 7 left, which is null, there the value of level would have been 4 plus 1, 5. So you should not get intimidated by that, right? So just ignore nulls, okay? But whenever you are at a node, which is your leaf, you can detect that in this manner. If both the left and right pointers are null, it means that my current node is a leaf node. If it is my leaf node, there will be some level at this point, so I'll update my answer. I'll say that, hey, answer is equals to max of answer comma L, and then I can just return because there is nothing below it, no use of making further calls. Otherwise, if you are at nodes like 2, nodes like 1, nodes like maybe 5 or 1, wherever you are, which are neither nulls nor leaves, then you just first move to your left subtree and then you move to the right subtree by changing your levels in proper manner. And we know that whenever we go to our children, our level increases just by 1 unit. So what I can do is that I can first maybe go towards my left, and there I'll call get max height. I'll pass the pointer to the root of my left subtree, and along with that, the level of that, which is L plus 1. And let us pass the answer variable. And similarly, whenever I call for my right subtree, let me call recursively again, pass the reference to the root of my right subtree, which is root right, and then pass the level and pass this answer variable by reference. So guys, here this is void function, so there is nothing which is being returned. I just am updating my answer whenever I reach a condition which should prompt me to update my answer, which is my leaf conditions, right? So this approach can also be adopted and it will have the same time and complexity. Okay, cool.